Alright, so last time we talked about strain being defined at a point as opposed to being defined over a finite length. Like in undergraduate, you think of it as change in length over length, but we really need to start thinking more of it in terms of a continuum, where in fact it describes the deformation in the vicinity of the point. So last time we looked at the normal strain. This is like a stretching, and showed that the normal strain could be given as follows. So here the normal strains in the x, y, and z direction are simply partial derivatives of the displacement in that direction with respect to x, y, or z respectively. Okay? Alright, so now what I want to talk about to finish this up is the second type of deformation, or straining, which is shear. Okay? Alright? And if you remember the picture with shear strains, what happens is we have an initial cube of material. This has to be defined in the plane. So this has a length of delta x and a height of delta y. Again, this is really at a point. So we're going to take this in the limit as delta x and delta y go to 0. So it's a little cube of material, but it deforms, arbitrarily. So maybe the edges might move to some point here. But then there's also a shearing process where the edges actually distort. Okay? Let's see if I can get this right. All right? So instead of remaining a cube, it becomes this sort of oblique rhombus. Okay? And in this case, we look at the angle changes. Let's call this angle phi1 and this distortion angle, actually let's call this one phi1 and this one phi2. And we define the engineering shear strain, gamma, as the sum of phi1 plus phi2. So if it stays a square, then the shear strain is 0. So it's a measure of the distortion. Okay. All right. So again, what we want to do is we actually want to get this in terms of the displacement field. In this case, it might be a function of x and y. And then, there's also displacements in the y direction of x and y. Right. So the actual displacement vector is u in x and y direction. That's in the I direction plus v in the j direction. All right? So we want to be able to get this again as a function of position, just like we did with the normal strain. All right, so let's look at this again. So if I define this distance here, the amount that this moved up as delta 2, and the amount this edge has moved over from this point as delta 1, you can see that we can define theta 1, which is approximately the tangent of theta 1 for small angles, and that's defined as delta 1 over dy. So that's delta 1 over delta y. And likewise, we can get theta 2, which is approximately equal to the tangent of theta 2, which is delta 2 over big delta x. Okay? So how do we get delta 1 and delta 2? Well, if you look at, you can do Taylor series expansion, but I'll kind of do a little hand waving to make it go a little quicker. If you look at delta 1 is a displacement in the x direction, okay? But it comes about because of a change in the y, okay? So delta 1 is the change in the x displacement with respect to y multiplied by that finite distance delta y, okay? Plus, technically I should say, right, this is plus order terms delta y squared and higher. Likewise, delta 2 is a displacement in the y direction, but it comes about because we're moving in x. So it's the partial of the y displacement, v, with respect to x, times delta x, and that's terms delta x squared and higher. All right? So now you can see what we have. So this gives me, using this into here, I can easily get that phi1 is this term divided by delta y. So that gives me the partial of u with respect to y plus terms that are order delta y and higher. And likewise, using this form of delta x in for phi2, I can get that phi2 is the partial of v with respect to x plus terms that are order delta x and higher. So if we ignore the higher order terms, right, we can get gamma is phi1 and phi2. So that's basically, well, let's leave it. It's the partial of the displacement in the x direction with respect to y plus the partial of the displacement in the y direction with respect to x plus terms that are order delta y or delta x, linear delta y, delta x. So this is our definition of shear strain in the xy plane. So you see it's purely a function of the deformation. It's defined at a point. You get it right from the displacement fields, the displacement of the y and the displacement of the x. Okay? So in general, if you want to do a three-dimensional case, this is really, I should say, the engineering shear strain in the xy plane. Likewise, you could also have engineering shear strain in the yz plane. You could do a similar drawing and derive it, but from analogy, this would be the partial derivative of the displacement in the y direction with respect to z plus the partial derivative of the displacement in the z direction with respect to y. And then also you can get an engineering shear strain in the zx plane, and that would be the partial of the displacement in the z direction with respect to x plus the partial of the displacement in the x direction with respect to z. Okay? So just to summarize, to write all the strain components in terms of a displacement field. So if you're given the displacement fields in the x, y, and z directions respectively, we can compute the normal strains as follows. And the shear strains in the planes as follows. Shear strain in the YZ and then the shear strain in the ZX. That's awful. ZX. Partial of the displacement in the Z direction with respect to X plus the partial of the displacement in the X direction with respect to Z. Okay? So that's the actual mathematical definition of the strains in terms of the displacement field. So again, just to reiterate, you don't have to consider what the change in length over length is with the angle change. If you're given the displacement fields, you can exactly compute the strain field at the point. Okay? Okay. Let me stop there, and then I'll do an example in the next video real quick. Okay?